In this section, we shall talk about various aspects of operationalizing fairness in healthcare AI. We start the discussion from the perspective of fairness from a machine learning pipeline perspective. Being good is easy. What is difficult is being just. From the perspective of various strategies which can be applied across the spectrum of building machine learning models, we can divide these into three parts for bias mitigation: pre-processing, in-processing, and post-processing. So these correspond to where we do the intervention for bias mitigation. Is it before building the model, that's pre-processing, while the model is being built, in processing, or after the model has been built, which corresponds to post-processing? In pre-processing, we focus on mitigating bias before the model has been built. There are a number of schemes to do that, so we'll highlight a few of these. In reweighing, we generate weights for the training data for each protected variable to ensure that we have fairness before classification. In another scheme known as optimized preprocessing, we learn probabilistic transformations that minimally transforms the data while controlling for discrimination and limiting distortion in individual data samples. Thirdly, in learning fair representations, we find latent representations that encode the data well while obfuscating information about protected attributes. And lastly, in disparate impact remover, we edit features to increase group fairness while preserving rank ordering within groups. Fair ML via in-processing has a relatively extensive literature. In the interest of time and focus, we shall only discuss two of these representative techniques. In adversarial debiasing, we learn a classification model that simultaneously maximizes predictive performance and reduces an adversary's ability to determine the protected attributes. Since the approach minimizes information that can be used to determine proxies for discrimination, mainly with respect to an adversary, so it leads to a fair classifier. In prejudice removal via regularization, we add a discrimination-aware regularization term to the learning objective. So that's a standard way of basically doing regularization. Post-processing techniques in fair ML, they are also relatively extensive. And again, we will only talk about a few of these representative ones. In equalized odds post-processing, we change a target variable with certain probabilities to optimize equalized odds. In calibrated equal odds post-processing, again, we optimize calibrated classifier scores to find probabilities with which to change target variables with an equalized odds objective. And thirdly, they are what are known as reject option classification. Basically, for a confidence band around the decision boundaries with the highest uncertainty, give favorable outcomes to the unprivileged groups and unfavorable outcomes to the privileged groups. This brings us to various healthcare considerations in operationalization. But first, we need to revisit outcome-based fairness metrics. Fairness metrics like group fairness metrics or even individual fairness metrics optimize for immediate outcomes. So for example, diagnosis of a particular disease, predicting risk of readmission, predicting length of stay, etc. However, downstream effects are much harder to quantify. If you really think about it, the purpose of fairness metrics is to quantify the extent of the problem, but that's actually not equal to solving the problem. We are only defining how bad the problem is, but not necessarily how it can be solved. The other important thing to call out over here is that impossibility theorems do not imply that fairness in machine learning is impossible, but rather that it is constrained by certain real-world limitations. So given the limitations that we have already defined, it is also important to emphasize that cost optimization is not equivalent to need-based optimization. So what do we mean by that statement? So let's unpack it. So think about the following. The algorithmic scores are a key input to decisions about future enrollment in care coordination plans. So for an illustrative use case, consider the following. Less healthy blacks are scored at similar risk scores to more healthy whites, which leads to disparities in program skewing. Algorithms' predictions on health needs is really a prediction on health costs. And so, at a given level of health, so measured by number of chronic illnesses, it's been observed that blacks generate lower costs than whites on average. So by that, what we, as an example from this particular paper, is 1,800 less uh, per year as compared to the other group. However, if we take apart how these costs correspond to, then we get a radically different picture, which is basically that black patients generate very different kind of costs. Fewer inpatient, surgical, and outpatient specialist costs, and more costs related to emergency visits and dialysis. So in this particular paper, Obermeyer suggests that these results suggest that the driving force behind the bias we detect is that black patients generate lesser medical expenses conditional on health even when we account for specific conditions. So in other words, optimizing for cost does not equal optimizing in such a way that it leads to fair outcomes. Another important thing to keep in mind is that treatment effect is not monotonic. So consider a use case where we focus on a predicted risk of some future outcome. So let's say healthcare needs, which in turn will be used to target policy interventions. But there, the assumption is that the treatment effect is monotonic. But in the real world, that's actually not always true. Uh, so, for example, at the same level of algorithmic predicted risk, blacks or black patients have significantly more illnesses burden than white patients. The manner in which Obermeyer and others measured this was to compute an overall measure of health status, which is the number of active chronic conditions, also known as comorbidity score. It's a metric which is used extensively in the medical literature to provide a comprehensive view of a patient's health by race, conditional on algorithmic risk score. Another place where fairness becomes complicated is stakeholder trade-off. It basically corresponds to the scenario that fairness may require trade-off between different stakeholders. Uh, in practical terms, what that means is that optimization for one subpopulation may de-optimize for another population and vice versa. Uh, Another additional complication is that even within the majority population, there may be subpopulations which are not explicitly defined, which may be vulnerable nonetheless. So for example, so far we have mainly talked about race, ethnicity, sex, and gender, but there's also the socioeconomic dimension. So let's say if you're focusing on one element, which is race, then even amongst the dominant race, there are going to be groups which are economically vulnerable, come from certain socioeconomic classes. And so that may be something which may get left out if we just focus on certain variables. As an illustrative example, consider the following, or no-show prediction that we talked about earlier. So what a clinician wants to optimize for may be different from what the staff planner maybe want to optimize for, which in turn may be different from, let's say, a patient from a marginalized community or group maybe want to optimize for. So in order to create truly equitable systems, these different stakeholders need to be involved in assessing such systems and coming with a solution uh, which tries to satisfy various conditions as much as possible. And we do acknowledge that in certain scenarios, it may just not be possible to satisfy everyone. But that said, it is still impossible to, or rather important to have that discussion. So, which brings us to the various technical challenges and healthcare impact. So, we start the discussion with the issues related to fairness and calibration of machine learning models. Uh, so, calibration for a particular model corresponds to the following. Let's say we are making a prediction for a particular outcome for a set of people. So the set of people who received a predicted probability score of P, then the fraction of P members of this set should be positive instances. And so in the context of fairness, we can start that. So fairness between two groups, G1 and G2, let's say it could be black and white patients. So implies that for this calibration condition to hold simultaneously, it is just not possible to satisfy it for certain notions of fairness and still have a calibrated classifier. Another issue is underspecification. Underspecification corresponds to the scenario where multiple machine learning models can have roughly the same predictive performance in trained tests, but they can vary widely in performance when deployed. Uh, so a quote from a widely publicized paper from Google that an ML pipeline is underspecified if there are many predictors that a pipeline could return with similar predictive risk. However, if we do stress tests, then we discover that there is variability in distribution of errors across different populations, even though the overall predictive performance may be similar. Another interesting thing is that if you do stress tests, then some of the stress tests may actually be at odds with each other. So consider the particular task of imaging. So models that may be good at recognizing, let's say, pixelated images may be bad at recognizing images with high contrast and vice versa. So these stress tests, they have to be designed very carefully and intelligently. So what is the implication of fairness? For fairness, what this means is that when we have predictive multiplicity and under specification, then the choice of the models, it can impact fairness and lead to unfair models. So related to the some of the last few issues that we described is another concept known as fairness gerrymandering or intersectionality. So far, whenever we have talked about the concept of fairness, it has been mainly with respect to a particular protected variable. So it's race, ethnicity, sex, gender, so on and so forth. However, in the real world, people do not just have one particular attribute, they have multiple attributes, and these attributes can intersect. So think about factors like race, class, gender, and how they apply to a particular individual. So according to the Oxford Dictionary of the English Language, intersectionality refers to the interconnected nature of social categories. Uh, so the issue is that intersectionality is susceptible to fairness gerrymandering. It may be intentional or inadvertent. The issue is that the classifier appears to be fair on each individual group, but not for subgroups. So what does this have implications for fairness? What this means is that if we consider different statistical notions of fairness, then we can actually expand this to exponential or infinitely many subgroups. Uh, and that has actually been done in the literature. That is to generalize these different notions of fairness. But that also runs into different problems. So if we infinitely continue dissecting groups, then we will end up with groups of one, which is basically the individual. That may not be very useful. So there's this tension between, well, the level of granularity that one has to consider versus what can be useful, what can be statistically sound. Uh, so the computational problem of auditing subgroups for equality, for false positive rates, statistical parity, it's been observed that it's been shown that it's equivalent to the problem of weak agnostic learning. And that's another way of saying that it's computationally hard in the worst case. So that's the bad news. But the good news is that uh, because they are solutions for that problem with common good heuristics for sufficiently good uh, solutions, then we can apply those uh, so that we can address this problem in practice. All right. So to address the problem of intersectionality, different forms of notions of fairness have been defined. Um, so one is differential fairness. So here's one definition. So a mechanism is epsilon differentially fair with respect to a if the following conditions hold, where theta the distributions and the tuples which are given for the protected attribute values, the theta distributions correspond to those. So if we can generate that, then we can ensure differential fairness. That said, it should be noted that work on intersectional fairness in machine learning is relatively scarce. And it's important to call out that mainly one of the reason is the limitations with respect to data and some of the practical aspects of defining where to draw the line. Then there's also the concept of multi-accuracy, which uh, can be applied to intersectionality. It's basically a strong notion of subgroup fairness where it states that model should be unbiased overall as well as on every identifiable subpopulation. And there are algorithms where given a black box access to a classifier and a relatively small validation set, it is possible to audit such systems and create relatively unbiased sets. So suppose your model reveals that the predictor does not satisfy multi-accuracy, then one can post-process the classifier to create a new classifier that is multi-accurate without adversely affecting, let's say, the subpopulation on which the models were already accurate. So as an example, consider the following. So for this particular use case, the researchers created a synthetic disease outcome for each subgroup, uh, which was based on real-world data set that they had access to. And then for each subgroup, they created a set of synthetic binary labels using different polynomial functions. So the data set that this is coming from is the United Kingdom Biobank semi-synthetic data set. And what they observed was that using these techniques, it is possible to create models which were relatively accurate. So another thing to note is that so far when we have discussed fairness, we have mainly talked about the outcomes. Another notion of fairness which some researchers have talked about is with respect to the process fairness. That is, the process through which we talked about fairness should be fair and not just the outcome. Uh, so one proposal to measure that is that with respect to estimating the degree to which people consider usage of various features to be fair in the model. So mainly appealing to people's individual moral sense. So suppose, let's say we have a set of uh, people, uh, members of the society denoted by the set U. F denotes the set of all possible features that may be considered. Then uh, we can define the following. So feature a priori fairness. So basically without a priori knowledge of how features usage affect outcomes. So we ask people what features can be used, and then based on that, what people give answers to, we compute this metric. Okay, so and then there are different ways to further define that. So there's feature accuracy fairness. So fair to use if, let's say, a variable increases the accuracy of a classifier. Fair to use if it increases a measure of disparity. So to add some additional context, so the idea over here is that so we have a set of variables and we have a set of people, and we ask these people if it is possible to use certain variables in a model, or not possible, rather fair. Uh, and so we first ask them in general. So suppose, let's say, a protected feature like race, gender, age, it's fair to use these variables. If the answer So the answer may be positive or negative. And then we ask the same question, but now we tell them that using that particular variable, it may actually improve the outcome um, for everyone. Or let's say it improves the outcome for the minority group. How does that answer change? Uh, and so what these researchers did was that, so choosing based on these responses, so they chose a set of features, and based on that, they built a set of 512 classifiers for very low value of process fairness. So consider the vertically spread cluster on the left in all of these three figures. One could achieve all possible values of accuracy. However, upon further investigation, we also see that the three clusters correspond to classifier when features judged to be highly unfair. So gender, race, and age were present in the classifier feature set. And it's also possible to achieve high accuracy or high process fairness, but not necessarily both simultaneously. So in other words, process fairness also exhibits performance fairness trade-offs. Another important technique is using decoupled classifiers. So here's the scenario. So there are certain models that ignore group membership, uh, and while doing so, they impose heterogeneous trade-offs with respect to, let's say, performance or error across groups. The idea behind decoupled classifiers is that, what if we train classifier for each group using data from it? So they come up with certain performance guarantees. So it means that, well, decoupling would recover the most accurate classifier for each group. And a set of decoupled classifiers satisfies rationality. That is, if each group is assigned a model that is at least as accurate as, let's say, the pooled classifier. The main intuition is that our goal in general should be to use the sensitive attributes in such a manner that you're able to train the most accurate model, or model with the best predictive performance for each group without harming any group. That said, from a practical perspective, an important call out is that if you're not careful, then uh, there may be subpopulations which do not have sufficient amount of data, and so in those cases, those subpopulations may actually be harmed instead of benefiting from this technique. Another important technique to call out is adversarial debiasing. So the idea is that we simultaneously reduce data bias and model bias via adversarial networks. The idea is as follows. So we sample features and reformulate input with only non-sensitive features. Uh, And so while doing that, what we are doing is minimizing the marginal contribution of the sensitive features to strengthen the model robustness towards the sensitive feature. So what's the result? Well, adding sensitive information does not influence prediction results. And so what we end up doing is that, so we improve fairness as well as prediction performance. Um, and so this is one of the reasons why adversarial machine learning is widely used in learning fair representations. So now moving along the machine learning life cycle. So we focus on post-deployment issues. Real-world data is characterized by non-stationarity. So which is the concept that the distribution of the data may change over time. So this is what we talked about concept drift or data drift. And so there are different scenarios to think about and even characterize what constitutes stationarity and non-stationarity. So if you're using older data to predict most recent data, then if you split by time, then that's a non-stationary scenario. If you split randomly, then that's a stationary scenario. If you are doing one set of patients to predict another set of patients, so split by patient, so that's another non-stationary scenario. One very interesting result is that uh, from this widely cited paper is that using the model on future data, then it appears that a substantially simpler model is best. So this does not necessarily come with theoretical results, but this has been observed in a number of settings. So what are the implications for fairness? So one, uh, as we observed previously, is that a simpler model may actually not be the bad one. And in terms of just practical algorithms, in the literature, it's been shown that there are extended versions of machine learning algorithms that can deal with concept drift while being fair. So this becomes a non-issue. But that said, something to be aware of. So one way to address this is compute fairness metric known as fairness gain. Um, so it comes from information theory. So the idea is that the fairness gain of an attribute relative to instances D can be defined as the discrimination reduction in D due to splitting A. So this builds on the notion of information gain and related concept in information theory. Okay, so now this brings us to another interesting concept that we have to deal with. So exploration versus exploitation. So in machine learning, in certain domains, so we can do A/B testing, run uh, trials. That's not always possible in healthcare and medicine. So that limits exploration for ethical, moral, and practical reasons. Um, that said, unfortunately, that has not certain people uh, to actually venture in that direction. So as we talked about in the foundation section, there are examples of blatant violation of the Hippocratic Oath to that effect. So it's important to emphasize again that this is something uh, to keep in mind while designing such systems. Another really very interesting concept is that could it be the case that that fairness in AI systems may end up obfuscating fair outcomes? So what do we mean by that? Consider the following. So due to complexity of real-world healthcare use cases, uh, so these use cases, so the predictors may not map onto real-world causal relationships. So if that's the case, then guaranteeing fairness in predictions is actually not the same as guaranteeing fair outcomes, even while ignoring the post-deployment part. So if a model's performance is associated with, let's say, true events, not just, uh, let's say, train and testing and the variables associated with that, then, well, it would imply that most notions of model performance may suffer. But that said, because in a lot of these use cases in healthcare, it may take a long time for them to become evident. They may not be detectable given the fast-paced nature of machine learning. So that's where having a human in the loop and carefully considering these problems, it becomes very important. Uh, so one high-level conclusion is that fairness as measured by outcome metrics is insufficient. because there are always going to be real-world downstream effects of decision making, which must be carefully considered. Uh, so one instance of obfuscation could be that suppose we are trying to reduce the effect of a certain bias within an ML system. So that may be the case for the short run, but let's say for another type of bias, we may obfuscate persistent unfairness for, let's say, a longer time scale. And last but certainly not the least, one important issue is thinking about fairness-related issues while moving from high resource to low resource environment. This is actually a practical limitation of deploying machine learning models. Uh, so in most use cases, when we move from the production environment to deployment, then we observe a shift in performance. Um, but this shift is much more pronounced if we move from high resource environments to low resource environments. And so here we have to ask the question, well, what are the regulatory obligations and resource supports needed to ensure that the translation of technology happens, quote unquote, correctly? Because it's not just fairness, but other aspects of responsible AI actually break down. So to illustrate, consider the following example. So a few years ago, so Google developed this model for predicting diabetic retinopathy. So basically looking at image of a retina, it could predict if some patient has diabetes or not. This model was in fact railed as one of the first great successes of deep learning in healthcare and medicine. It had vastly superior performance as compared to a human physician. However, when it was deployed in the developing world, it was observed that the performance was less than stellar. So, for example, in certain remote villages in India, it was observed that the results for the study were slower, uh, less than optimal because uh, the internet connections they were, let's say, unreliable. Uh, it, Another assumption was that all the images that we're using in training, they were in a setting with sufficient amount of light and excellent conditions, while in the real world, let's say in a rural setting in a room in a developing parts of the world where with limited electricity, um, it's not the same environment in terms of getting the same amount of data. So in one instance, they observed that the internet went out for 2 hours, so the patients they actually had to wait. So one of the goals was to deploying this system was to speed up uh, patient screening. In this particular case, in fact, it slowed it down, and so as an end result, fewer people received treatment. So these and other related issues. So that's very important when thinking about such problems in a holistic manner.